Welcome all of you to the class. So in the last lecture we discussed how one can realize efficient implementations using polyphase representation, Nobel identities, the identity on interconnected systems, etc., right, and then using all these tricks how we can realize efficient architectures for rational sampling rate conversion. And one of the important considerations in the design of high decimation filters is the following issue. Suppose I give you a decimation rate of a huge factor, say 100 or 1000 to be realized. Some questions that naturally arise to us is do we just do some filtering followed by downsampling by a huge factor, say 100 or 1000, or do you want to break this into different components where I have filtering followed by downsampling by 10 and then another downsampling by 10 so on, or maybe filtering then downsampling by 10, another filtering downsampling by 10, and what are the considerations, right. So this is some thought one would get, but let us go a little bit into the details of these architectures and see if there is any benefit of multi-stage decimation or expansion or interpolation accordingly. So let us start with some schematics here. I have a sample discrete time signal. Let us say the sampling frequency at the input is f0, and at this stage we are filtering, so we are preserving the sampling rate. We downsample this by a rate m, and we have the signal here at a rate f0 upon m, right, and I will say this is architecture 1. This is a normal thing, right. I mean, I have a discrete time signal, I filter it with some filter, typically a low pass filter with some cutoff and some transition band, and then you downsample this by a factor of m. You might even argue why do this way if I start with this architecture. That means at the input it is the same, I have this filter h of n, instead I decompose this m into some rates m1, m2 dot some mi. This is my y of n. M is basically broken down into capital I number of stages, and we know what happens to the frequency response at the output of each of these downsamples. We know those effects, right. So this is possibly another architecture architecture 2, and both of these architectures guarantee us at the output we are still at a rate f naught upon m, right, and this is f naught. At this stage it is also f naught. Now you might think about a third architecture, which is I have some filter followed by downsampler, I cascade it with another filter followed by downsampler, and so on and so forth. Filtering is doing some kind of operations where I basically filter out certain frequencies, but the downsampling rate at the output, the net downsampling rate at the output is somehow to be preserved at capital M, that is desired per architecture 1, right. So, let us draw the schematic. So, we have x of n. Now, this is a little different than 1 and 2. So, we have some h1n followed by downsampling rate m1 dot 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 till we can go to I stages if we want to, or we could just restrict it to some say p stages. So, these are cascaded stages, and the net sampling rate at this stage is f naught upon m. So, this is the idea behind multistage implementation, but you may ask this question to start with. It seems obvious that we are greatly increasing the computations by having many intermediate filters at various stages. So, this is opposite to our intention. Okay. The goal would be to show why multistage structures are advantageous over a single stage. But at this stage still you may get a thought in your mind that if I really have a very narrow transition band, right, the filter order that I would require would be humongous. With a single stage, let us say I am looking at a signal say 10 kilohertz sampled and I want to downsample it by some rate 100 say suppose, and I want a very narrow transition band to accomplish this filtering. So, the question is, if I use a single stage, we know obviously that the filter order would be very high, but using multi-stage designs, is it somehow possible to reduce the filter order? That is the key thing here. If you realize, you would reduce the filter order somehow using lower order filters at various stages, yet you have to accomplish the specifications of what is required for your design. Okay. So, let us start with a design example that will make things very clear, right. I mean, at this moment it is sketchy, we have some thoughts for various architectures and the thought process is still sketchy for us because we are not very sure exactly which is the right direction to go about. So, we will see with a 2-stage design and then we will convince ourselves why this is the right way to go about. So, let us consider a signal x of n with sampling rate 10 kilohertz is to be downsampled by a factor m equals 100. So, when we downsample this by a factor 100, we get a signal at 100 hertz, right, to produce a signal at 100 hertz. The pass band of the signal is from 0 to 45 hertz and the band from 45 to 50 hertz is the transition band. And we are assuming equi-ripple filters. So, we also have some specifications on the ripple in the stop band and the pass band, and that is also part of the design spec. A pass band ripple of 0.01 and a stop band ripple of 0.001 are desired. I mean, let me put it, are required. That means you cannot overshoot this. So, if you just think about what this really translates, so this is our stop band delta S, this is our frequency f or omega. So, this is this is Fp in the pass band, this is Fs in the stop band, and this is a 0.5 is normalized frequencies, right, and this is pi at the Nyquist, omega s, omega p. And if this gain is to be 1, this would be 1 minus delta p, this is 1 plus delta p. Okay. So, this is the response, the frequency response. This is frequency response. On the y axis and on the x axis is your frequencies, right. This is what we need. So, the first and the foremost step that you will have to take is to estimate the filter order, right. So, we are given certain quantities and the quantities are omega s, omega p, right. The stop band is 50 hertz, this pass band cutoff here is about 45 hertz, and we need sharp attenuation after 50 hertz, okay, and we need 100 hertz is what is the output rate. So, we have the other parameters. So, the delta f, which you can compute directly, so let me say this is perhaps it's omega is 2 pi f. So, I think I can just put, I can call this as Fs, this is Fp, and I call delta f, and this is about 5 hertz, which is 50 minus 45. I mean omega is basically 2 pi f, and then you could normalize this. So, now we have to get the filter order for this problem, and for this we invoke this formula n equals 1 plus d infinity of delta p comma delta s, and I think I have to mention the other two parameters as well here. Delta p is 0.01 and delta s is 0.001. Okay. So, now we have all the specifications here. Now, from this we have to get towards estimating the filter order. So, we have an equation towards this, and I will provide you this formula and I will give you the reference. So, first let me write the reference. So, this comes from the work of Larry Rabiner from Bell Labs, from Bell Labs in 1970s, and this paper is basically titled Some Comparisons of FIR and IIR digital filters. This is from Bell System Technical Journal, volume 53, number 2, February, the issue 2 and February 1974. And let me give you what these formulas look like. So, d infinity of delta p comma delta s is a1 log delta p to base 10 square plus a2 log delta p plus a3 times log delta s plus a4 log delta p to base 10 square plus a5 log to base 10 delta p plus a6, and the parameters are a1 is 5.3 e minus 3, a2 is 0.071, a3 is minus 0.4761, a4 is minus 0.0026, a5 is minus 0.5941, a6 is minus 0.4278. It looks quite messy formula, and this is empirical. And there is also this term, and we can ignore this to some extent, but I'll write down the formula as well for what f is. We'll have to go to the next page. This is not enough. F of delta p comma delta s is 0.512 log to base 10 delta p over delta s plus 11.01. So, if you are interested in figuring out how they arrived at this formula, you can look into this paper which has some other reference papers, and that will give you some insight how this is done. This is an empirical formula, and there are some simplifications which are less accurate. I would mention this as less accurate, but simplified version, and that formula is n equal to minus 10 log to base 10 delta p times delta s minus 15 by 14 delta f plus 1. So, these details are given in Rabiner's work, but for all purposes for this design example we can ignore this term, we can ignore f, this function, that is this other approximation that we have, we will ignore this term and we will focus only on this. Okay. And you have all the numerics here, you have delta p, you have delta s, you have all the values, all the constants that are connecting. So, you can plug in to the formula, and if you are not comfortable with this formula, you could also use Belanger's formula which we gave, which I gave you earlier. That is also a formula that you can use, right. You can use whichever is your favorite. A small thing that I noticed here is it has to be delta f by f on this slide, and in the previous one as well, where we have this has to be delta f by f and delta f upon f, okay, so that the units come out correct. So, let us get towards computing these quantities. So, let us compute all the quantities from the specifications that we have. Okay. Now, n is approximately d infinity of delta p comma delta s. We ignore the -1 factor there, right, and we will say this is going to be delta f by f. So, if you plug in the delta p and delta s that we have, which is 0.01, 0.001 divided by delta f is 5 hertz, f is basically 10 kilohertz. So, you see the change here, 5 hertz is the transition band, 10 kilohertz is your input rate, and that is why things get skewed so much. So, you do the math and the answer to this would be 5080. It is a tremendous filter order, 5000 is the order of the filter that you would require. This is a practical problem, right. I had a 10 kilohertz signal and I wanted to downsample it by 100 and I have very narrow transition band of 5 hertz, and if I did all the math, this is what I will land up with. So, now you can imagine the latencies etc. that this filter will cause if you were to implement them. Now, let us look at the multiplications required per second needed to implement this. The number of multiplications per second needed to implement this would be n times f over 2m. I mean I am bringing this factor 2, I think you can question why. Possibly by exploiting filter symmetry or other properties. So, assume you can do something clever. So, I am bringing this factor 2 and that factor 2 would hold good for any multi-stage filter. So, that is something which you have to bear in mind, but if you are not comfortable putting this factor 2 is still okay, right. If you did the blunt way without any optimization or any special tricks on the FIR filter, you would just have a factor NF upon M, okay. So, just to make you aware of that factor 2 that why we need. So, if you just plug in these values, the filter order we computed to be 5080 times sampling rate 10 kilohertz divided by downsampling rate is 100, just this factor 2 that would appear. And if you did this, it roughly comes to about 2.54 mega multiplications per second. This is quite a lot. You are burning and you just compute with your circuit elements what it would take to burn this much power per second. It is a lot. So, you are wasting power because your multiplications are huge. Second, you have to consume a lot of area if you were to put this into via silicon, right, because the filter order is huge and you have to basically have all those taps stored, and then what about leakage and many other factors that you have to bring in, right. So, this is not a good solution. Okay. So, this is for single stage design. And this is not very efficient. Okay. So, let us see if we can do this slightly differently. Now, from the intuition we have from architecture 3, right. So, architecture 2 is still no good because you have the base filter which is 5000 length long, and then if you just filter it with that, still you are going to burn that, you know, the that much amount of power because you are filtering through a filter which is of huge filter order, right. So, we still think architecture 2 is going to be no good, except that you could perhaps simplify certain things spectrally by using a cascade of these downsamplers. But let us directly plunge into architecture 3 and see how we can get any benefit. So, we have x of n which is at rate 10 kilohertz. So, we first subject this to a low pass filter 1, let us say this order is n1. Now, I can write downsampling by 100 as downsampling by 50 and downsampling by 2, I could do that. So, the first stage, let me downsample this by 50, then I take this to another low pass filter 2, then I downsample this by a rate 2 and then I get y of n, and let us say this order is n2. Okay. So, let us look at some interim points. So, if you have 10 kilohertz and you are downsampling by 50, at this step you are at 200 hertz rate, right, and from 200 hertz if you downsample by 2 you are at 100 hertz rate, which is what is desired, right. So, now from 10 kilohertz you are at 200, from 200 you are at 100. Now, what we require is some specifications to the filters, right, that is a missing piece, some specifications to the filters, because I have not given you the specifications of your individual multi-stage filters. I gave you an overall specification of what the desired frequency response has to be, right. So, one can think about the following here. For this stage, I am keeping it flat, but you know, just imagine in your mind sort of some ripples here. Let us assume that this is 45 to 150, right. I am stretching my transition band, right. Instead of having 45 to 50 in the original, I am making it 45 to 150, and this is as usual 45, is probably sharper, 45 to 50. Okay. So, this is some careful detail that you will have to note. So, here this is for LP F1, this is for LP F2. Transition band extends from 45 hertz to 150 hertz, and this is advantageous to us because if we stretch the transition band, the lower the filter order, right. So, this makes sense, but there is another issue that you have to worry about is the aliasing, because if you had this rate at 200 hertz, right, that is your rate is for 200 hertz, your Nyquist would be at 100. So, if the Nyquist is at 100 hertz, any all those frequencies from 100 to 150 hertz would be aliased back between 50 to 100 hertz here, and our intuition should tell us that if we eliminate 50 to 100 hertz using another low pass filter here, we are removing the aliased components. Clear? So, I mean, while drawing this response, two things have to be borne in mind. One is the transition band, because this controls the filter order, but sampling rate at output is 200 hertz, which implies aliasing of frequencies from 100 to 150 hertz to the 50 to 100 hertz band. Which sort of motivates us to go to filter 2, which is this low pass filter, to remove aliasing energy or aliased components, right. This energy is aliased here, we want to remove the aliased components, and that sort of gives us the idea why we need the second low pass filter to be within 45 to 50. I mean, this is the transition band, 45 to 50 hertz is the transition band. Okay. So, let us do our computations for this design. Now, there is a little bit of detail on the ripples. So, we saw the frequency domain effects both in terms of aliasing as well as in the transition band, and we have to also see what happens to the ripples. So, this is from observations. Passband ripple for each stage is approximately delta p upon 2, because when you cascade the passband ripples add up, and stop band ripple only gets reduced So, therefore, we are okay to leave our stop band to delta s, but the pass band we have to consider it to be delta p upon 2 for individual filters. Okay. Now, let us look at the first stage. So, for the first stage n1 is approximately d infinity of delta p upon 2 comma delta s divided by, now the transition band delta f is now 150 minus 45 and your frequency at the input is 10 kilohertz. And if you did the math, this would give us 263. So, where was 5080 and where we are at 263, right? And you could do your multiplications per second for stage 1 is equal to NF upon, again we will assume some factor 2 here, assuming that the filter is done efficiently. I will just mark it with a circle. If you are not comfortable, you do not have to use this 2, it is perfectly fine. So, this would give us 263 times 10 kilohertz upon 2 times 50. Right, and whatever that number is. Now, so I will just write this as from what I have is 52,600 by 2 multiplications per second. Just this factor 2 appears the way it is. Now, let us look at the second stage. For the second stage, we do the same way. N2 is d infinity of delta p comma delta s. So, for delta p upon 2 comma delta s, and the transition band is between 50 and 45 hertz divided by the input rate is now 200 hertz, right. We had 10 kilohertz, we downsampled it by a rate of 50 and the rate was 200, I mean we were at 200 hertz and that is downsampled by 2, that is, and we have 100. So, therefore, this is 200 here because this is the input for the second stage, and you do the math for this is approximately 111 taps. I mean this is the order of the filter, and you do the multiplications per second. This is 111 times 200 divided by 2 times 2. 2 is your M2 here, right. So, this is I will leave it as 11,000 divided by 2. This 2 factor appears all the time. I just would put this, I just mark this by red. If you are not comfortable, you do not have to use this factor. this is the number of multiplications per second. So, now the overall computations for the two stage design is, we said it was 52,600, I guess, 52,600 plus 11,000 1/2. So many multiplications per second, and this is assuming some filter symmetry that we want to bring in to simplify this design. So, I think if we just compare what we have here versus the single stage design which had this 2.54 mega multiplications versus something that we have in the order of about 60,000 by 2, which is about 30,000 multiplications, right. It is a factor of 1:8. So, this is something which we have to bear in mind. So, comparing to the single stage design, we have nearly 8:1 improvement, and this is really significant. This is like 8x of improvement that we have with a two stage design. And one can imagine that in the early stages the sampling rates are high, and equivalently the transition widths are also large, leading to smaller values of the filter length, and in the last stage the sampling rate and transition widths tend to be smaller, giving lower orders, but possibly comparable to the earlier stages. Okay. So, this is something which you have to note. So, let us list some advantages and disadvantages of multi-stage architectures. So, first is significantly reduced computations, and we saw this through the example. Then the filter taps are also less, right, because the order is less. So, therefore, it is reduced storage. Then our filter design is also simplified. And I think one of the most important things that people often ignore is you never have floating point when you think about implementation, it is fixed point. So, therefore, when you think about such filters, they are subject to finite word length effects, and if you think about the quantization noise, you have to look at what is the implication of quantization. When you quantize every filter and you take an input noise and you filter it through this filter, I mean it is going to be colored because of this filtering, and the variance also would be higher. So, therefore, it is important to have reduced filter orders, so that we have reduced finite word length effects, and therefore lower round of noise and sensitivity issues. This is very important, and particularly if you are launching a satellite, putting these filters etc., you have to be very careful about quantization effects. So reduced finite word length effects, which means lower round of noise and coefficient sensitivity. Now if we were to even think of drawbacks, I would not say really there are any drawbacks, it is a win-win situation, but I think it is but we just have to list pondering about it. So one is increased control structure required to implement the design. I mean, you have to be slightly clever how you stitch the blocks together. There will be timing issues and many other things that you will have to take care. It is a little bit of implementation detail, and I think then you have to really do your design over all choice of MIs. For example, if I want to realize 100, I might do it 50 times 2, I may do example 100 could be realized as I will just put this in this form. Hundred is 10 times 10, 100 is 25 times 4, 100 is 20 times 5, and we also looked at the case where 100 is 50 times 2. I mean, there are all possible combinations of, if you were to think about a 2-stage design, whether you want to downsample by 50 first or 10 or 25 or 20 and then cascade it with either 2, 10, 4 or 5, right. You have all these choices that you will have to think and ponder upon. You will have to do this. I mean, I think that is, I do not see it is a drawback, it is just a burden on the designer to be a little more efficient and clever to exercise this control. Okay. So I think this completes this lecture on multi-stage implementations for realizing high rate decimation filters, and hopefully you find this topic useful when we actually build circuits and design and do design architectures for multi-rate systems with multi-stage designs. Okay.